Alright, in the previous video, I covered why series solutions are important in the real world. In this video, I'll cover how to exactly solve differential equations with series solutions. So suppose we have the differential equation y double prime minus y equals 0. Pretty simple. You could solve this using characteristics equations, but I'll solve using series solutions. So since I said in the previous video we're working with polynomials, this is going to be the form of equation that we have, a of n x to the n. So these infinite series, they work awfully similar to Taylor series. So say we have like the special function sine of x. While sine of x is also an infinite series, it can also be an infinite series, a of n x to the n. And this is, if you expand it out, it should be x minus x cubed over 3 factorial, x to the 5th over 5 factorial, and so on, where the coefficients, we know what the coefficients are. So the point of series solutions is to find the coefficients. So how do we solve this? Well, we could first differentiate y. So that would be d dx of the whole series. So if you differentiate the whole series, well, that's the same thing as taking the sum of every single individual term differentiated. So you can just bring the d dx inside the series and it still works out. So you have all this times n x to n minus 1. However, you should note that whenever you have series like this, you know y goes in this form. That would be, if you expand it out, it's like a0, a1x plus a2x squared, so on. But whenever you differentiate a constant, it goes to 0. So this constant goes to 0. So basically that would mean that you have to start off on the first term rather than the 0th term, because the 0th term just goes to 0, so you don't even need to keep it. So then you can, you can differentiate y prime to find y double prime. So y double prime, you can change the index again, start off at 2, go to infinity. This time you'll have a to the n times n minus 1, x to the n minus 2. You're just using power rule. And this is all possible because n is just a constant, a of n is just a constant. So you could just differentiate with respect to x and you'll be fine. Okay, so to progress, we can plug y double prime and y into the differential equation. So let's do that. So we have n equals 2 to infinity, a of n, and n minus 1, x to the n minus 2, minus infinite series, infinity, n equals 0, a of n, x to the n equals 0. Okay, now what you can do is you can shift the index down to 0. So but in order to keep it the same algebraically, then you have to shift all the indices inside, or you have to shift all the n's up by 2. So you have a of n plus 2 now, just to make sure that you start off at n equals 2. Then you have n plus 2. Then you have n plus 2 minus 1, so that would be n plus 1, x to the n, minus infinite series. This stays the same. Okay, so to continue, I'll get rid of all this. Well, due to the linearity of these series, you can just add these two series up and it will be the same because both of them start at 0 and end at infinity. So you have n equals 0 to infinity of a of n plus 2, n plus 2, n plus 1, x to the n minus a to the n, x to the n equals 0. But if you paid attention in your pre-calculus class or wherever you learned this, you should know that in order for a series to equal 0, in order for a whole series to equal 0, each individual term has to be 0. at least for this case. Because even if you have just one non-zero term, it'll be like x to the third times 1. Well, nothing can really cancel it out because everything is of higher term. Everything is of higher or lower polynomial term, and so we won't be able to cancel this out. So every single individual term has to be 0. So that's awfully convenient for us because now we can disregard this infinite series sign because we know that each individual term must be 0. So we can keep this. Then we could just transfer this over to the other side. We could divide by x to the n. And since this is really a game of solving for the coefficients, we end up getting a of n plus 2 equals a of n over n plus 2, n plus 1. So in this case, when we end up with something like that, there's no solution, or there's no formula to give us a of 0 and a of 1. So we have to determine it ourselves. And we could just say that a of 0, a of 1 are both, 1. Make it convenient for us. It can really be whatever you want. And a of n plus 2 and all the future terms will just have to conform with this formula and these initial terms that we set. And it'll be a solution for y. So, okay, so let's say that we could set a of 0 and a of 1 to be whatever it is we want. So a of 0 is 1, then that'll be 1, plus a of 1, we set it to be 1, so that'll be 1 times x, or x. Now, to solve for a of 2, we have to plug 0 into n. So a2 equals a0 over 0 plus 2, 0 plus 1. So that'll be 1/2. So 1/2 x squared. And then to solve for a of 3, we have to plug a of 1 in. We get 3 times 2. That would be 1/6. We could find a of 4. That would be a2 over 2 plus 1 over 2 plus 2. So 2 is 1/2 over 3 times 4, 12. So you'd have 1 over 24, x to the 4th, and so on. So point is, if you choose you can choose the initial terms, and everything that follows will have to obey the rules. So the rule that we found was that a of n plus 2 equals a over n plus 1, n plus 2. So if you make this go all the way to infinity, you'll find an exact solution to this differential equation, but in the real world, you won't be able to find exact solutions because computers don't have infinite computing power. So most likely, what a computer will do is they'll find all the coefficients and then they'll cut it off up to a certain threshold, and they'll cut it off. So it could be like n equals, it depends. It could be like n equals 100, for example. And then you'll have a polynomial that goes all the way to 100 terms. It really varies. So that's all for today, and I'll see you in the next video. Thank you.